This is a 5-minute introduction to the QM-Maxima package. This package uses the Maxima computer algebra system, which is available for free on SourceForge. And I'm also using the WX-Maxima interface for Maxima, and that provides this nice interface with a cell-based structure and so on. The QM-Maxima package is a third-party package. It's not part of Maxima, but it's available from my GitHub website, which is shown here. And QM-Maxima focuses on quantum mechanics calculations for finite-dimensional Hilbert spaces. So this is typically spins, 1/2, 1, 3/2, and so on, that have finite-dimensional Hilbert spaces. We can construct things like tensor products with these particles and do multi-particle calculations. We can calculate things including Stern-Gerlach amplitudes for Stern-Gerlach experiments and so on. So let me just kind of give you a very quick introduction. So loading QM-Maxima is quite easy. You have to have the paths set up in Maxima to find the package wherever you have it located. But once you do that, it's just as easy as typing load QM, and then because we are using WX-Maxima, I will also load WX-Lisp, which helps with the pretty printing of the kets and bras in the WX-Maxima interface. So there are two types of kets and bras in QM-Maxima, depending on what you want to do. So we can create kets and bras that are completely abstract. So if I say ket and I input it with a list A, B, it will display a ket. And this is an abstract ket. There's no matrix representation. And A and B are two states. And these can be interpreted, pretty widely here. So these are just generic states. And if we create a bra, let's say CD, it will look like a bra here with CD as the list of states. And if we want to take the bracket, so we could take bra of CD, and the non-commutative dot operator in Maxima is shown here, and this will provide, this will be the ket, the bracket. So this will give us a bracket, and so for completely arbitrary or abstract kets and bras, they're assumed to be orthonormal. So here we have bra CD with ket AB will give us a Kronecker delta on AC and a Kronecker delta BD. So those are the abstract kets, and we can do things. For example, we have Bell states, so an entangled Bell state. Whoops, will look like so. So this is the up-down minus down-up state. This is the Bell entangled state. You can work with that state doing various things. So for example, we could create the density operator for this particular state by saying Bell 1 and dot that with the dagger. So we're going to take the adjoint of that state, Bell 1. This is rho, so this is the density matrix, and we can calculate, for example, the matrix representation. So if I say I want the matrix representation of rho and I have to give it a basis, what basis? Well, I'm going to say there's another function called basis set. It contains two particles and they're labeled by 0 and 1. That will give us the basis set, and so we can calculate the matrix representation of rho. So you can take partial traces and find subdensity matrices and so on. And this is the abstract representation of the kets. Now, let's do the matrix representation of the kets. So if we have a specific system in mind, let's suppose it's the spin 1/2 system. So predefined in the spin half system, we have Z plus, Z minus kets, X plus, X minus, and Y plus, Y minus, so we can see what they all look like. So z plus and z minus are just the 1, 0, 0, 1 column vectors. X plus minus are what you expect, and the same with y plus minus. And you can do calculations with these, for example, Stern-Gerlach type experiments using spin operators. So within the spin 1/2 system, we have the following matrix operators defined, so Sx, Sy, and Sz, and these will all be written in the z basis. So you can look in your textbooks and see that these are in fact Sx, Sy, and Sz. And for larger spin, we can calculate these operators, say Sx for 3/2 spin 3/2 gives us the Sx matrix for spin 3/2. If you want to calculate the kets for a particular spin, we could, for example, we could ask for spin mket, that means matrix-based ket, and let's suppose we want it for spin, let's do spin 1, and this would be this first number is the total spin, the second number is the spin projection upon the z-axis, and then which ket do I want? Let's do the y ket, for example. So that is 2, and that's the ket in that. That's the spin mket for spin 1. That's the y ket. Okay, so that's how you make basic states in the abstract and matrix representation. Let me finish with just making a general mket. So if I want to make a general mket, I can do that by, if I do ABC for my ket, it just creates a column vector with A, B, and C. Okay, so let's stop there, and I'll pick up with the next section in a moment.